Page 376, Chapter 10, Lesson 1, Forms of Energy. Science FNT, Chapter 10, Lesson 1, page 376, Forms of Energy. The main idea or essential question. Energy takes many forms. Energy can be changed from one form to another, but it cannot be created or destroyed. Copy it. Efficiency, page 379. The efficiency of a machine compares the amount of work a machine does to the amount of energy put into the machine. So efficiency, work machine does, VS period, which means versus, work machine does versus energy put in. Energy, page 376. Scientists define energy as the ability to do work. Energy, ability to do work. Solar energy. For example, energy from the sun is called solar energy. Solar energy, energy from sun. Energy transformations. Energy transformations. Wherever you look, you see the effects of energy. Cars driving by in the street. So example given, cars driving. Kids playing basketball. Kids playing. Water boiling on the stove. Water boiling. All these depend on some form of energy. Energy is vital to life and to our society. The United States government even has a Department of Energy. But what is energy? Energy is a basic component of the universe. Basic component of universe. It is everywhere. Scientists define energy as the ability to do work. Ability to do work. Energy comes in many forms. For example, energy from the sun is called solar energy. Forms, solar. Energy that a chemical reaction can release is called chemical energy. Chemical. Energy from position or motion is called mechanical energy. Mechanical. A coiled spring has mechanical energy, as does a hit baseball. All right, energy changes at a cookout. As wood burns, its chemical energy is changed into thermal energy and radiant energy. The teens will gain energy from the food they eat. Okay, so draw a picture. Wood burns. There's some little logs and fire, and it says wood burns. It said chemical energy is changed into thermal and radiant. So chemical goes in. Thermal, which is heat, comes out. Radiant, which is light, comes out. And then remember, they also said the teens gain energy from the food they eat. So food is a chemical type of energy. So chemical, food. Okay, make that drawing. Energy changes in a car. This car burns gasoline in its engine. The chemical energy in the gasoline is changed into mechanical energy. Some of the energy is lost as thermal energy. Okay, draw yourself a little car. Chemical energy, the gas goes in. Mechanical energy, the going, or the vroom vroom, the go. Let's go, comes out. And then thermal, or heat, also comes out. That's what they meant when they said lost as thermal energy. There's that thermal heat. Okay, energy can be changed or transformed from one form to another. Can change form. When this happens, thermal energy is released. Arrow releases thermal energy. In a car, for example, engine parts become hot because of friction. The thermal energy released in the engine cannot be used to do useful work. Parentheses, often not useful. Close parentheses. That thermal energy is often not useful. Electricity is another form of energy. Go back up here to forms and add electrical. Electrical energy is changed into other forms, in devices such as light bulbs, toasters, radios, and fans. Much of modern technology relies on energy changing form, as shown in the drawing above. This drawing. Okay? Modern technology relies on changing form. Examples include any device that burns fuel or that runs on electricity. Okay? We're going to do this, but not the entire thing. We're going to say here is where the energy is going in. We're boiling water. So boil water. That causes steam. So steam. The steam makes this turbine turn. So turbine generator. It generates electricity. So out comes electricity. Okay, so how do we boil the water? Well, we need thermal energy, right? We need fire. So now your whole drawing should start with thermal energy. That heat boils the water. The boiling water can change into steam. The steam flows and makes the turbine generator spin, and it generates electricity. And then we can use that electricity for all the things we plug in. All right, let's see. Next up. Energy transformations also play important roles in nature. Nature. Radiant energy from the sun warms Earth and powers weather. Radiant sun, arrow, weather. Plants use solar energy from the sun to grow. Solar energy, arrow, plants grow. Plants also convert solar energy into chemical energy, which is stored in food they produce. So an arrow from the plants grow, chemical energy stored equals quote-unquote food. When the plants are eaten, this chemical energy is changed by the consumer into different forms of energy needed to carry out life processes. Okay, how might conditions on Earth be different if energy could not change form? If energy could not change form, then plants and nature would not be able to operate because there would be no photosynthesis, so no food. We wouldn't have a lot of modern technology that relies on changing forms. We probably wouldn't have electricity. We probably wouldn't have cars. We probably couldn't even burn some wood just to stay warm or get some light. So we would be missing a basic component of the universe, and simple things like driving a car or playing outside or boiling some water wouldn't even exist. Okay, next page. Conservation of energy. Conservation of energy. Do you think a machine, such as an electric motor, could produce the same amount of mechanical energy as the amount of electrical energy used to make it run? No, this cannot happen. In every energy transformation, some energy is always lost as thermal energy. Some energy lost, thermal. The total amount of energy still exists, but it is not all used by the machine to do work. So that thermal energy provides no work. The energy that's lost as thermal energy usually provides no work. It's just heat that gets lost. Think about pushing a friend on a swing. You push hard until your friend is swinging quite high. The force of your push has given the swing and its rider mechanical energy. What happens when you stop pushing? The swing will slow down and eventually stop. Friction between the air and your friend's body will change the mechanical energy of the moving swing to thermal energy. Okay, so an example given, swing stops because of friction. So we'll friction between the chains of the swing and the frame, up here where the chain connects. In any closed system, one in which energy cannot enter or exit, the total amount of energy remains the same. Energy can change form, but it cannot be created or destroyed. Okay, we already have that in our main idea, cannot be created or destroyed. These two concepts make up the law of conservation of energy. The law of ... conservation of energy. All machines illustrate this law. Machines may take up energy from fossil fuels, electricity, or even the energy stored in your body. Yet that energy does not disappear. Often it is converted to thermal energy. Okay, when the adult pushes on the swing, energy is transferred to set the swing in motion. When she stops pushing, the swing will slow to a stop. So she has to keep putting energy in. That energy keeps getting lost as friction between the boy and the air or between the chains and the frame. For years, people have tried to build machines that run forever without any energy input. Why is this an impossible dream? Well, now we know about friction, and friction losing thermal energy. So they call it perpetual motion. See that up here? Perpetual motion. No perpetual motion. Okay, flip it over. Energy efficiency. As you have learned, some thermal energy is always produced when energy changes form. Because of this, most machines are not very energy efficient. Thermal loss is not efficient. The efficiency of a machine compares the amount of work a machine does to the amount of energy put into the machine. So work vs period versus energy input. Work versus energy input. Efficiency is usually expressed as a ratio of the energy output of a machine to the energy input. No machine can be 100% efficient. No machine 100% efficient. Some simple machines, such as levers or pulleys, can come close. Because little friction is involved, the output of such machines can be almost as great as the input. However, the more moving parts a machine uses, the less efficient it is, mainly because of increased friction. So, more moving parts, arrow up, less efficient, arrow down. The more moving parts you have, the less efficient that machine becomes. Consider an electric power system, such as the one shown in the diagram above. The output of the system is the delivery of electricity to people's homes. The input is the energy used to produce and deliver that electricity. By the time the electricity energy reaches your home, only a small fraction of the energy input is left. And when you turn on a light, only part of the electrical energy is changed to light. Okay, so let's do that. Energy input, 100%. Power plant, energy lost. Power plant. You only get about 30% out to the electrical lines, 30% out to the electrical lines, 20% goes to the house, 20% goes to the house, and then you get even less when you turn on something like a light bulb. So, think of all the wood, coal, natural gas, or whatever we're putting into these power plants to generate electricity, and we lose 70% of that just to get it over the power lines. We lose another 10% just to get it to the houses, and then we lose even more when we turn something on in the house. All that energy is getting lost to heat. Most of the electric energy flowing through the bulb is converted to thermal energy. The bulb gets hot. Thermal loss. Exclamation point, circle it. How can energy efficiency be improved? Power plants can reduce friction in turbines and generators. Reduce friction. They can also reduce energy losses along power lines. Reduce loss. Customers, in turn, can use energy-saving devices such as compact fluorescent lights. Energy-saving devices. Okay, compact fluorescent lights. You might see them at the store, and they're called CFL. Back when I was a little kid, and sometimes some light bulbs today still have it, where there's a little thin piece of wire inside the bulb, and when you turn the light on, it heats up and it glows bright orange or white. Those are the old style of bulbs called incandescent. But if you have the ones that are like a tube of glass, and they flicker when you turn them on. Or if you have the ones like here in our classroom, LED lights, they actually look like this. Those are little LEDs, light emitting diodes. Those are much more energy efficient than the incandescent bulbs. Okay, why should energy efficiency be improved? Energy efficiency should be improved because we are losing a lot of energy to thermal loss. If we can use that energy and conserve it or have more efficient machines, then we can use less energy overall, which means we have to put less in to get more out. All right, next page. Oh wait, as energy is converted from one form to another and distributed to different places, some energy is lost as thermal energy at each step. Okay, that's what we drew. Demand for energy use. Demand for energy use. As the world's population has grown, the demand for energy has risen. For centuries, people relied on wood as their main source of energy. Centuries relied on wood. However, that changed drastically during the Industrial Revolution of the 19th century. The new machines and factories of this era ran not on wood, but on coal. Industrial Revolution, coal. Hey, sounds like Minecraft. You start with wood, but eventually you get to have furnaces and other things that run on coal. As the graph shows, they're talking about this graph, the use of coal rose sharply during the late 1800s. Okay, let's look at that. Coal is the blue line. Coal, as the 1800s, the late 1800s, all of a sudden it ramps up. And here in the early 1900s and up until today, coal is used a lot. As new technologies developed, the use of other fossil fuels rose as well. New tech led to other fuels. During the 20th century, that means the 1900s, people became more aware of problems that widespread use of fossil fuels has caused. This awareness sparked interest in alternative energy sources. Alternative, such as hydroelectric energy. Hydroelectric. Hydro means water, electric means electricity. So when they build a dam like the Hoover Dam and the water flows through and spins the motor to create electricity, that's hydroelectric. Very similar to this, but instead of heating up the water, they just let the river run through it to spin the turbine. Where were we? And nuclear energy. Nuclear. You'll read about them later in this chapter. Today, the United States makes up about 5% of the world's population. U.S., 5% population. Yet the country uses about 26% of the world's energy. But 26% energy, exclamation point. Think about that. We are only 5% of the world, and we use 26% of the world's energy. We are energy hogs. As developing countries grow and become more industrialized, their energy use likely will increase. As population goes up, energy use goes up a lot. 3 arrows up. How do you think the U.S. and global demand for energy will change? Explain. I think U.S. and global demand for energy will increase because developing countries will need more energy. As populations go up, energy use goes up. As new technologies are invented, we have to come up with other types of fuels to power them. Okay, looking at the graph, red is petroleum, that's like oil. So notice how high oil goes. That's all the people driving their cars and oil-fueled power plants. Orange is natural gas. Natural gas is going up and getting used more. That's for heating your home or also power plants for electricity. Coal and blue. Coal went up early on because that was the first one people learned how to use. It's basically like really dense wood, lots of energy in it. Yellow is nuclear. We've invented a little bit, but people are scared of it and it's hard to control, so we haven't used that much. Hydroelectric, there's some, but the problem is it relies on damming up rivers, which hurts the fish in the environment. And then purple is the wood. Well, we used to use wood, and now we just kind of use about the same amount of wood because we figured out how to use alternative forms. Over the past 150 years, the use of energy has risen dramatically. All U.S. cities have changed, much like San Francisco, shown in the photographs. 1860s, that's 150 years ago. Wood shacks, they probably just used candles or burned some wood. Today, look at all those lights. They're lighting up bridges, they're lighting up streets, they're lighting up buildings. It's the middle of the night and all these people have all these lights on. All that electricity running all night, every year. 24 hours a day, 7 days a week, 365 days a year, every year of our lives. All that electricity is being used. That's why we're using so many resources. Okay, that's phase 1, taking the notes. So, phase 2, processing. We're going to use the visual summary to highlight. Then we're going to use the main idea to annotate with red stars. Okay, energy can change from one form to another. Energy, form, can be changed. Energy transformation. The wood burning are examples of energy transformations. Can change form. And I think that's about it for that. At a campfire, chemical energy stored in the wood is changed to thermal energy and light energy. Okay? Chemical energy in the wood becomes thermal heat and radiant light. All moving objects carry energy, as do waves. Okay, well, mechanical is moving, so highlight mechanical. As energy is converted and distributed, some energy is always lost as heat. Conservation of energy, some energy lost, thermal. Thermal loss. Energy efficiency. For this reason, energy efficiency is always less than 100%. Energy efficiency, no machine 100% efficient. For centuries, people relied on wood as their main source of energy. Centuries relied on wood. Today, fossil fuels and other energy sources power modern technology. New tech, other fuels, alternative. Demand for energy use. Okay, cannot be created or destroyed. And efficiency. All right, now let's do the red annotating. Energy, forms, can be changed, cannot be created or destroyed. Energy, the example of the wood burning. Energy does work, can change form, and there are different forms. The example of the car, that's another example of how energy can be changed. The example of using boiling water to get steam to spin a turbine to make electricity. There's another can be changed. Okay, let's see. Some energy is lost as thermal energy, right? It's not being created or destroyed, but it can change forms. No perpetual motion. Work versus energy input. So efficiency is how much work it does versus how much energy you have to put into it. There's always thermal loss, and no machine's 100% efficient. And then with new tech comes new fuels that we need to use. All right, phase 3, connect thinking. Do not write something that's on this paper. Write something that's inside your brain and put it in your e-binder. Okay? It has to be related to forms of energy. Don't tell me about your cat unless you're talking about how your cat changes energy from the chemical form of food that it eats to the mechanical form of running or the mechanical form of breathing. Even if it's just laying there napping, it's still breathing and its heart is still pumping. All right. I predict. Make a prediction and tell me why. Why is that prediction? What do you predict? Here's a good one. What do you predict about our energy use in the future? What do you predict about alternative types of fuels we might come up with? Okay, phase 4, writing the summary. Let's talk out loud about a summary. Energy takes many forms. Energy can be changed from one form to another, but it cannot be created or destroyed. Energy is the ability to do work, In other words, to grow plants, or burn wood and provide heat and light, or maybe move something, or power something electrically. Okay? Some energy is always lost as thermal heat. There's no such thing as perpetual motion. Right? No machine can be 100% efficient because there's always some thermal loss. As people invent new technologies, we also have to come up with new and alternative sources of fuel for that energy. All right, there you go. Good job persevering with a growth mindset, and roar, Wildcats.